Clocks and memory question, for a change of scene. This is an absolutely typical clocks and memory question in that it's full of utter nonsense. It's a perfectly simple question made to look difficult by nonsense, and you shouldn't be taken in for a minute. What have we? We've got Disco Mary. It's just an excuse to make up a name. Rummaging through a collection of old electronic spare parts. She finds a multicolour lamp. Here's the lamp. And it's got 3 inputs labelled red, green, and blue. The red input signal is not yet connected to anything. The green input signal is connected to the output of a T flip-flop. So here's the green T. It's got a T and a Q that I've labelled G for green, as well as writing them in green. And similarly, the blue input signal is connected to the output of another T flip-flop. It's a thing I do, by the way, in order to spare myself the pain of drawing a diagram, is that I would describe a circuit for you in words and ask you to draw the diagram. That requires reading the words. It's sometimes quite arduous. The same clock signal generator feeds both the clock inputs, and the T inputs are not yet connected. So this is the thing that Disco Mary has found. Okay, so for part A, let's get part A on the page. Mary remembers that combining red, green, and blue light gives white, while switching just one of those signals off gives cyan, magenta, and yellow, respectively. Tabulate the possible input signals for the lamp and indicate which color display each will generate. So we've got red, green, and blue. And I better draw a truth table. So we'll have 0 and 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. So let's see if we can figure out what's going on here. If we say, don't be red, don't be green, and don't be blue, what colour will come out of the lamp? None at all, it'll be off. I will accept off, black, none, any of those things. If we just have the blue input on, what colour will come out? Shocking. How about just green?
Green.
Green and blue? So green and blue will produce cyan. And it even tells you, right? So red, green, and blue, right? If you switch one of them off, cyan, magenta, and yellow respectively, it's telling you that if you switch red off, you get cyan. If we have just red coming in, we'll get red light out. If we have red and blue, we will get magenta, which is a fancy kind of purple. If we have red and green but not blue, we'll get yellow. And if we have all 3, white. Welcome to the colour choices of 1980s home computers. The cheap ones at that. Okay. Part B, give the characteristic table for a T flip-flop. Fine. Characteristic table, that means we've got a column for the t signal at time t. We don't have a column for q of t, but we do have a column for q of t plus 1, which can be expressed in terms of q of t. Tabulate all possible controls, 0 or 1. What happens to q of t plus 1 when t is 0? Well, remember, t means toggle, and we're saying don't toggle, so that means it stays the same. So we put q of t there. What happens if t is 1? Then it will toggle, so we get that q of t plus 1 is not q of t. So whatever it was at time t, it will be the opposite at time t plus 1. Okay, so that's hopefully marks for reading and marks for bookwork. What happens next? More nonsense. Mary's favourite song is What a Blue Sunset by Ray Dayglow and the Thunderclaps, which is completely useless information. So she decides to wire the lamp and flip-flops to make a repeating sequence of colours, changing with each clock cycle. Ah, finally some information. We have cyan, blue, yellow, red, then back to cyan and round again. Okay, so what we need to do, what we're told, is let QG of t be the state of the flip-flop controlling the green input signal at time t, with QB correspondingly for blue. So that's what I've drawn here, QG, QB. Construct a truth table showing for each possible pair if we know what they are at time t, what do they have to be at time t plus 1? If Mary's colour sequence is to happen as planned, it may help to include columns for the red signal at these times as well. Let's take that hint and figure it out. So we're going to need a column for r of t and r of t plus 1. We're going to need a column for qg of t and qg of t plus 1. We're going to need a column for qb of t and qb of t plus 1. Okay, so let's get this right. Let's fold this. Right, so what we care about are the situations where we're in Mary's colour scheme. So if we're in so we go cyan, I folded the wrong thing. We want to go cyan, then blue, then yellow, then red, then back to cyan. So let's first of all plot the cyan situation. We said cyan is 0, 1, 1. So if we're in cyan, we're in 0, 1, 1. What do we go to after cyan? Blue. So what are the signals going to be for blue? 0, 0, 1. Okay, suppose we're in 0, 0, 1. What do we go to next? Yellow. And what would yellow be? 1, 1, 0. Suppose we're in 1, 1, 0. So that means yellow. Where do we go to next? 1, 0, 0. All right. And suppose we're in, so that's red. Suppose we're in red. Where do we go to next? 0, 1, 1, back to cyan. So we've got that when we can see from these two columns here what change happens each time. Do you notice anything in particular about the red columns? it's just not blue. So if we know how to control blue, and we have some NOT gates handy, we'll be able to control red at the same time. Okay? So all that matters is green or blue. Okay, I've painted myself into a little bit of a corner by drawing those boxes, because what I want to do is add some columns for TG of T and TB of T. Okay? So what we need to do in each situation is figure out what change is happening to each of the flip-flops. And then if we know what change is happening, we ought to be able to figure out which T signal would make that change happen. Okay? That's how you do these questions. You look at the change that's supposed to happen, and then you figure out how to tell it to happen. Okay? So for example, when we're on the top line, what's happening to the green flip-flop? Is it toggling or not? Yes, it's toggling. What signal do we send to make it do that? 1. What about the next line? Toggling or not? Yes, it's toggling, so we send 1. Toggling or not? It's toggling, send a 1. Toggling or not? It's toggling, send a 1. That's good news. We figured out that the green flip-flop is always toggling. Okay, what about the blue one? Toggling or not? Not. How do we make that happen? Send a 0. Toggling or not? It's toggling, so we send a 1. Toggling or not? It's not toggling, it's staying 0, so we send 0 to tell it not to toggle. Toggling or not? That one's toggling, so we need to send a 1. Okay, so we now have a truth table that tells us what the T signals have to be given what the Q signals are. And that means we've figured out enough logic to build the control circuitry. Okay. So indeed that was we've just done C part 1. C part 2, Mary rummages further and finds some wire, 2 NOT gates, and a source of logic 1. She is delighted because she knows she can complete her circuit without breaking any existing connections. She can extend existing connections by joining further wires. Draw a carefully labelled diagram to show how she can make the lamp display her chosen repeating sequence. Okay, now I made the mistake of drawing this too near the top of the page, so I'd better draw it again. Here's the lamp. We got red, we got green, we got blue, we got a T flip-flop for that, and we got a T flip-flop here. This is the green one. This is the blue one. Okay. So, let's look at our green T flip-flop. What does its T signal need to be? The T signal for the green flip-flop is always 1. And we've been told that we have a source of logic 1, because I must have been feeling particularly kind whilst I made up this question in the bath that day. So in goes logic 1 to the green T flip-flop, which means it will always toggle. As we figured out, it always must. Okay. How about the T signal for the blue flip-flop?
Not Q of G.
Yes, you can see that TB is 0101 exactly when QG is 1010. So TB is always not of QG. So that's good. We've got one more thing to do. We need to control the red input. But what did we say about the red input? Right, this is the information we've got, these two columns. We have to control this.
It's not blue.
It's not blue. That's exactly what we've got here. So that's Disco Mary's disco light sequence for What a Blue Sunset, built successfully. Everyone see how that worked? It's one of those things, you just got to keep calm, read the question, figure out, the question will tell you what is supposed to happen, and then you have to work back from what is supposed to happen to which T signal, or which input signals to the flip-flops cause the behavior that's being asked for. And once you've done that, you've got a straight up ordinary logic gate problem where you've got some signals at time t and you've got to compute some other signals at the same time. So once you've got everything into the same time, you're just doing an ordinary logic circuits problem. And here it's noticing, oh goodness me, TG is always 1, TB is always not QG, R is always not QB. So then it's just building some circuitry that has that outcome. Okay, so the main problem with these questions is that you have to read them. They're not going to work if you just try to kind of react to a question by producing some stuff from your memorization of the teaching materials, because it's not going to be there. I mean, there'll be a couple of marks where it is, where you got, you're asked to produce one of these things or something like that. But for the rest of it, it's not going to be a thing you can remember. It's a thing you've got to figure out from the description. But it's always the same deal. First of all, figure out what behavior is needed, then figure out what signals would produce that behavior, then figure out what circuit would produce those control signals. That's what's going on. That's always the method. Okay.